As an engineer, consider that you have to construct a 100-story tall concrete building or a bridge with excellent fair-face finishes. Is it possible to specify conventional concrete with 50 mm slump value? The answer is definitely no. In such cases, we have to introduce a relatively new type of advanced concrete, self-compacting or self-consolidating concrete, SCC. As implied by its name, SCC does not require vibration and therefore does not produce noise. It achieves concrete compaction into every part of the formwork simply by means of its own weight and without segregation of the coarse aggregate. Different to cement, aggregates and water you design in conventional concrete using standards such as British Department of Environment, DOE, American Concrete Institute, ACI, or absolute volume approach. SCC does not have a standard design method. It is mostly based on trial and error experience and feeding test data back to the design. The major purpose of SCC is to increase the ease and rate of concrete flow. Normally, SCC requires the following. Firstly, the addition of superplasticizer for the deflocculation and dispersion of cement particles to happen. And secondly, we should add pozzolans such as fly ash so that the pozzolans can effectively disperse over and get absorbed on cement. Thirdly, we have to increase the fine aggregate to total aggregate ratio when compared to normal concrete. For example, from 0.42 to 0.50 to reduce overall viscosity. To test SCC, we measure the abilities for the SCC to flow, to fill, to pass, and to resist a segregation. These SCC's abilities are commonly characterized by 4 common tests: the L-box test, the slump flow test, the J-ring test, and the wet sieving stabilities test. First, we introduce the L-box test, which measures the filling and passing abilities of SCC. For conducting the L-box test, you will need a scoop, a stopwatch, a measuring tape, a shovel, a moist cloth, a leveler, and a L-shaped box with 3 steel bars separating the vertical and horizontal portion of the box. The steel bars should be spaced at least 3 times more than the maximum aggregate size to make sure the bar spacing does not block aggregates passing through. These bars serve to simulate reinforcements in actual site condition, which hinders the passage of SCC. There are 3 steps to follow in the test. The first step is preparation. The second step is molding. And the last step is measurement. Now watch each step carefully. The first step is preparation. A. Dampen the L box with moist cloth. B. Level the base of L box with a leveler. And C. Close the door separating the vertical and horizontal portions in the L box. The second step is molding. D. Place the concrete in the vertical portion of the L box until it reaches the top. E. Strike off the surface of the concrete by means of a shovel. F. Remove a spilled concrete from the L box. G. Open the door between the vertical and horizontal portions of the box, and thus the concrete is allowed to flow through a line of vertical reinforcing bars and into the horizontal portion of the box. The third step is measurement. H. After the concrete comes to rest in the apparatus, the heights of the concrete at the end of the horizontal portion, H2, and in the vertical section, H1, are measured to determine the block ratio, H2 to H1. If the SCC is truly self-leveling, the value of the block ratio will be 1. A minimum acceptable value is 0.8. A value larger than 1 represents segregation. A concrete sample with coarse aggregates reaching the far end of the horizontal part of the box exhibits good resistance to segregation. The second test is the slump flow test, which measures the ability of SCC to flow. For conducting this test, you will need a slump cone, a leveler, a steel rod, a measuring tape, a base plate, and a stopwatch. Again, we follow the 3-step procedures: preparation, molding, and measurement. The first step is preparation. A. Dampen the slump cone with moist cloth. B. Level the base plate with the leveler. C. Rest the slump cone on the surface or at the center of the base plate. The second step is molding. D. Hold the cone firmly in place during filling. E. Fill the cone with concrete in one lift. F. Keep the concrete above the top of the cone. G. Keep the top layer of concrete. H. Add more concrete to keep an excess above the top of the cone. I. Remove spilled concrete from the base plate. The third step is measurement. J. Raise the cone by a steady vertical lift with no lateral or torsional motion. Simultaneously, start the stopwatch and record the T50 time taken to reach the 500 mm spread circle. K. Now wait of the resulting circular flow of concrete. Measure the diameters to the nearest 5 mm. L. Measure a second diameter of the circular flow approximately perpendicular to the first measured diameter. M. Take an average of the slump flow from the two measured diameters. The higher the slump flow value, the greater is the ability to fill in the formwork under its own weight. The slump flow value must reach at least because it takes less time to reach the 500 mm spread circle. 3 to 7 seconds is acceptable for civil engineering application. Is suitable for housing application. The third test is the J-ring test, which measures the fill-in and passing ability of SCC. The procedures are exactly the same as the slump flow test, except that a J-ring is used. The J-ring must rest outside concentrically to the slump cone. The steel bars of the J-ring serve to simulate reinforcements in actual site condition, which hinders the passage of SCC. Next, if the slump flow test and the J-ring test are carried out together, we can assess the block of SCC. We can do it by calculating the difference between the J-ring flow and the slump flow to the nearest 10 mm. This difference gives a measure of blocking assessment, which represent the passing ability of the SCC. Also, you should note that the slump flow and J-ring test must be completed within 6 minutes. We set a time limit to avoid excessive slump loss. The fourth test is the wet sieving stability, which measures the segregation resistance ability of SCC. For conducting this test, you will need a bucket with at least 10 litre volume, a sieve pan, a stopwatch, a 5 mm sieve, and a balance readable to 1 gram. Let us follow the 3-step procedures: preparation, casting, and measurement. The first step is preparation. A 10 litre sample of concrete is placed inside a bucket and allowed to sit for 15 minutes to allow any segregation to occur. B. Seal the bucket to prevent evaporation. C. Put the sieving pan and 5 mm sieve on the balance and set the reading of the balance at 0. The second step is casting. D. After sitting for 15 minutes, approximately the top 2 litre is poured from the bucket from a height of 500 mm onto a 5 mm sieve. E. The concrete is allowed to flow through the sieve into the sieve pan for 2 minutes. The third step is measurement. F. Weigh the mass MA poured onto the sieve and the mass MB in the sieve pan. Then calculate the segregation ratio. The segregation ratio should be between 5 and 15% for acceptable segregation resistance. Concrete with a segregation ratio above 15% would exhibit too much segregation, while concrete with a ratio below 5% is said to be excessively resistant. Therefore, either too high or too low ratio is not acceptable. This is the end of the procedures for the 4 tests. The tests are carried out much faster in actual cases. Watch the tests again at normal pace. See if you can follow each of these. So far, through the 4 tests we have introduced, we are able to characterize the SCC's abilities to flow, to fill, to pass, and the ability to resist segregation. SCC is a generic term for mixed designs. It differs from traditional concretes at the molecular interface between the cement compounds and the admixture. The fluidity of SCC ensures a high level of workability, while the rapid rate of placement provides an enhanced surface finish. But good workability does not sacrifice strength and durability. SCC's overnight strengths typically reach 30 to 40 megapascals, and 2-day strengths can even reach 100 megapascals. If the mix is well designed, durability is also enhanced because pozzolans are used to replace part of cement. SCC is certainly the way forward for both in situ and precast concrete construction. The health and safety benefits and the improved construction and performance results make it a very attractive solution. These tests and many others are discussed in detail and have been standardized in American Concrete Institute's committee reports. American Standard Testing of Materials, European Standards, and Hong Kong Construction Standard. By watching this short video, we hope you have been able to understand 3 main points. 1. The procedures to carry out the L-box, slump flow, J-ring, and wet sieving stability test. 2. The underlying principles of the mechanism of SCC. 3. The reasons for carrying out the SCC tests, such as evaluation of the abilities to flow, to fill, to pass, and to resist segregation. So next time when someone walks by a concrete skyscraper and wonders how amazing it is, then what is your answer? That's all for this video. Thanks for watching.